Okay, so let's start. It's my honor to introduce Professor Zohar Komargodski. Please forgive my bad pronunciation from the Simon Center, Economic University. His research covers many aspects of quantum field theory, including conformal field theory, phase theory, and supersymmetry. So please join me in welcoming Professor Zohar Komargodski.
Thank you very much. Oh, is it too loud? Thank you so much. Very, very happy to be here and very excited. It's my first time in BIMSA. I'll talk about some applications of the subject of defects, quantum field theory. So there will be some part about the theory, and there will be some part about applications. So this is ongoing work. Mostly I'll be mostly talking about this ongoing work with Maisam Barkeshli. He's a condensed matter theorist from the University of Maryland. Chris Fetchison, his student, and my student, Siwei Zhang. So this is some work that we've been doing over the last couple of months, and it will hopefully finish soon. So the introduction is that the local operators in quantum field theory are, of course, very important. And there has been plenty of research about understanding correlation functions and the dynamics of local operators. But a very important generalization is that there are extended operators in quantum field theory. These extended operators I will denote by D. And these extended operators are supported on some p-dimensional submanifolds. So these are the case of p equals to 0 is a local operator, and the case of p bigger than 0 is the case of extended operators. Now, while there has been decades of research on the properties of local operators, very little is known about extended operators. We don't know if there are infinitely many different extended operators. We don't know their spectra, and so on and so forth. So in many examples, almost nothing is known. A very important idea that is only relevant for extended operators is that we can place the extended operators in the time direction. So if the extended operators are lines or surfaces, we can choose one direction to be along time. And that means that there's a Hamiltonian formulation. So in a Hamiltonian formulation, an extended operator is like an impurity in space, which is why the subject is very relevant for various experiments and condensed matter problems. So we're essentially modifying the translational invariant Hamiltonian by some impurity that could be localized at a point or could be smeared on a line. And that means that there is a Hilbert space and there is a Hamiltonian that acts on this Hilbert space. And that is why extended operators have preferred normalization. You cannot take an extended operator and multiply it by square root of 2. That is not allowed, unlike local operators. Because for extended operators, we have this Hamiltonian picture. And when we place them along the time direction, there has to be a sensible Hilbert space. So extended operators have a preferred normalization. And we will see today that this leads to some important theorems about extended operators, renormalization group flows on extended operators, and so forth. So that idea is very important. By the way, if there are any questions, please stop me. So extended operators have this preferred normalization. So this is the picture. You can think about extended operators like line operators in space-time, or if you look more like condensed matter intuition or Hamiltonian intuition, you can think about them as some kind of impurities in space. So another thing you can do with these extended operators is you can multiply them by integers and you can form direct sums. So this is allowed. So the Hilbert space in the presence of a direct sum is just a direct sum of the Hilbert spaces. And physically, what does it mean? Sorry. What does it physically mean to do a direct sum of impurities? What it means physically is that the red impurity can be in several quantum states. And a direct sum means that this impurity has several quantum states, and the Hilbert space will be a direct sum of those possible quantum states. So these are natural operations that you can do with extended operators. You can multiply them by integers and make direct sums. Now, the impurity Hamiltonian has its own coupling constants because we modify the Hamiltonian. Or in other words, extended operators have their own coupling constants, which is not the case for local operators. So even if the bulk coupling constants are at the renormalization group fixed point, for instance, so if the bulk is conformal and there is no renormalization group evolution, it's still the case that there could be renormalization group evolution on the extended operator, on the impurity. And typically, the coupling constants on the impurity also reach a defect conformal filtering. So they reach a fixed point. They reach a fixed point, and we have a conformal filtering on the defect. So that's the notion of defect conformal filtering. It's the situation when both the Hamiltonian in the bulk and the Hamiltonian that's associated to this impurity are at a renormalization group fixed point. So there are many examples. I'll talk today for simplicity only on what we've been doing with these collaborators that I showed at the beginning. We've been looking at examples which are line defects and they correspond to local impurities in space. This is important because of condensed matter applications for defects in crystals, and I'll get to it at the end. So the Kondo defect is an example. Wilson and Hooft lines are examples. Pinning field defects are examples. But today I'll talk about symmetry defects, which are essentially solenoids. So we will consider modifying the Hamiltonian by inserting a solenoid and a Aharonov-Bohm solenoid, and crystalline defects, such as disclinations. And this will be the applications that I'll get to at the very end. Are there any questions? Okay. So I'm going to start from some very simple high school material. Quickly just remind you of the most important features of a solenoid, a Aharonov-Bohm solenoid, and then define what symmetry defects are. And then we'll discuss the subtleties in the renormalization group of solenoids. So the subject of today will be essentially to understand the renormalization group of solenoids, which is quite interesting. So we will find the boson with the solenoid, fermion with the solenoid. We'll prove some theorems about the normalization of these operators, and then I'll compare with some experiments and simulations. So this is the outline. So the main references that I'll be using today, except for this ongoing work, are these papers from very recently about related subjects. So the first paper is about the normalization of these operators, and these papers do some very important computations that I'll be using. So let's remember what is the quantum mechanical setup. This is just to set the stage. We have a particle of mass m moving on a ring of radius r, and we put a solenoid in the middle with flux phi. This is a very classic thing that you probably saw in undergrad. So the energy spectrum in quantum mechanics depends on the flux. This is an important result. And the eigenstates, the energy eigenstates have currents. So you can choose the energy eigenstate, and there's typically some current running around the solenoid. This is the formula for the current in this eigenstate. A very important thing is that there is a special choice of the flux, which is a half flux. The flux goes from 0 to 2 pi. You can choose the flux to be between 0 and 2 pi without loss of generality. And when you're exactly at the midpoint at pi, there are two degenerate ground states. And these two ground states are related by time reversal symmetry. If you follow a diabatic evolution, then the ground states have a current. This is the possible values of the current in the ground state. It depends how you do the adiabatic evolution, because there is a twofold degeneracy, but you may get a current, which is plus or minus a half times this expression. But because you can make general linear superpositions of the eigenstates, and you can get any current in this interval. One important thing is that only these eigenstates are homogeneous on the ring. If you make some superpositions of the eigenstates, for instance, a superposition where there is no current, that configuration is not going to be homogeneous when there is no current on average. Okay, so this is just very basic stuff about the Aharonov-Bohm effect that leads to currents running around the circle. Okay, so now let's talk about the more general situation. Let's consider any quantum field theory. We can define an extended operator, which we'll call which is codimension 1. Sorry. So let me just show you the picture. A symmetry defect is a codimension 1 surface with a boundary. So the boundary is codimension 2, and the bulk is codimension 1. So for any QFT with a global symmetry G, there is this extended operator which implements a symmetry transformation as you go around the boundary of the surface dg. So dg is essentially a solenoid. It's the quantum field theory generalization of a solenoid. It implements a symmetry G for all local operators. So that's the picture. This is codimension 1, and the boundary is codimension 2. Okay? So the boundary, we will not be, even though the whole thing is codimension 1, because this is a symmetry transformation, you can move the shape of this bulk to whatever you want. So this will not be very important for dynamics. The important thing for the dynamics is the boundary of the symmetry defect. If you want, we're looking at netter charges, but instead of integrating them over the whole space, we're just integrating them on some part of space. And then there is a boundary, and the boundary is going to behave like an interesting dynamical defect. Okay, this is the setup of what a symmetry defect is. So unless the symmetry is trivial, that's what I'm saying here, the defect is attached to a codimension 1 symmetry operator. But since it's topological, we will kind of ignore it. And therefore, we can think about symmetry defects as codimension 2 defects for all matters and purposes. In 2 + 1 dimensions, which is what I'm going to do today, so today will be in 2 + 1 dimensions, dg is therefore just a line defect, and therefore it's a local impurity in the Hamiltonian language, and the impurity is the solenoid. It's very simple. Let me just show you a picture. I'll get to the picture later. So we just put a solenoid in 2 + 1 dimensions in a Hamiltonian picture. Okay. This is technical comment I'll ignore. So have we finished defining what defects are we talking about? So this is the main point of the talk. The answer is that we haven't finished, because we just specified how various bulk fields transform, as we go around the defect. But it turns out that this is not enough to define the problem. Unlike in quantum mechanics, where this is enough, here specifying how local operators transform around the defect is not enough to define exactly what is the impurity that we're talking about. And the point is that now the bulk particles or waves, they can scatter from the solenoid. So they can actually pinch on the solenoid and scatter from it. So it turns out to be crucial to discuss the interactions of the solenoid with the bulk particles. So you can think that the solenoid, in addition to inserting some magnetic flux, also introduces some potential. And you can expand this potential as a local potential with some parameters u, u prime, and so forth. Yeah. So I'm only, for instance, the question was, why am I not including the first derivative of the delta function? because that would mean that the potential of the solenoid is not isotropic. So I'm just assuming that the solenoid is some isotropic object, which inserts magnetic flux, and particles can scatter from it. Oh, you can make, this is a space-time picture. So the solenoid is some line operator. But if you think about it in a Hamiltonian language, the solenoid is just a point. And so we're discussing the potential that this point leads to. If you want to have a very non-trivial shape in space-time, it means that somebody is shaking the solenoid. So that's an interesting experiment, but that would be more time-dependent. I'm not going to discuss it today. So I'm just going to discuss, I'm just going to discuss the simplest case. Yes, continuous electrons. Yes, it is true. It is topological, but the point is that our symmetry defect is an open manifold, and the boundary, which is codimension 2, is non-topological, and that is the physical solenoid. You see what I'm saying? So the Noether theorem only guarantees that the bulk is topological, but the boundary is not topological. The boundary is a genuine conformal defect, which is a physical impurity in your system. B, which so when you prepare a solenoid in the material, then it will have some B, right? You just make it from something, so it has some potential. Oh no, that's a property of what you mean by the impurity. The impurity is some solenoid, which leads to monodromies, and V is part of the definition of how you prepared this impurity. It's a parameter on the line defect. So you remember I said that the defects have their own parameters with their own renormalization group? So you should think about V as a coupling constant on the defect. Then it's a coupling constant. It's not about the states. It's about the coupling constant in the Hamiltonian of the defect. And now we will discuss how this gets renormalized. Yes. Yes, it's very good point. The defect has a fixed normalization because it has to lead to a Hilbert space. But as we know from quantum mechanics, we can change the Hamiltonian continuously while still maintaining a healthy Hilbert space. So this is a parameter in the Hamiltonian of the defect, and for any choice, because it's a local thing. So the normalization is global, and the Hamiltonian is local. So you can change the Hamiltonian and still maintain a healthy Hilbert space. And when I said normalization, maybe I could write an equation. So you could think that the defect Lagrangian is something like exponential. This is the action of the defect, okay? It's an exponential of some integral over some coupling constants, maybe. But the normalization is this number. You cannot put square root of 2 here, but you can change this. Okay, so let's try to understand how this gets renormalized. This could be in Landau-Lifshitz, but it's not in Landau-Lifshitz. So let's take a free boson. We have a free boson in 2 + 1 dimensions. And we put a solenoid. This is a solenoid at the origin. It's a flat connection with curvature only at the origin of space. And we include a potential. This is a free parameter. And you see that it's a coupling constant on the defect because there is a delta function. So there is a question, does this get renormalized? It's a quadratic field theory, and it's not hard to compute the beta function. This is the beta function. So if you put interaction u on the defect, sorry, this is for vanishing phi. So this is the beta function when there is no solenoid. So this is really elementary. You just take a free boson, you put a defect, which is some potential, and you ask how does this potential renormalize as you flow to the infrared. And this is renormalization in quantum mechanics, essentially. Okay, it's not even quantum filter. It's just renormalization in quantum mechanics because it's it's 0+1. And the answer is that if you have a delta function interaction in 2+1 dimensions, it's marginally irrelevant. So the interaction goes to 0. So it's an easy computation in a quadratic field theory. Now you can ask, how does the solenoid change the beta function? That's another easy computation, not as easy, but not difficult. And this is the exact beta function. It's a quadratic field theory, so the beta function is one loop exact. So this is the renormalization group evolution of this contact interaction. So let's analyze the fixed points. Phi is the flux. So you see that the flux changes the interaction evolution under the renormalization group. So just to be clear, I'm solving this problem. You can just give it as a graduate exercise. Free field theory with a contact interaction and find the beta function for this coupling. Very easy. So we have two fixed points because it's a quadratic beta function. One fixed point is a stable fixed point. And the stable fixed point, at the stable fixed point, there is an irrelevant operator with scaling dimension 1 plus the defect flux. So you see that the flux actually changes the scaling dimensions of operators near the solenoid. Another fixed point is unstable. It has a relevant operator with scaling dimension 1 minus phi over pi. And something funny happens when phi is equal to pi. It goes to 0, and this fixed point loses unitarity. So we see that there are two fixed points in the presence of a solenoid for a free boson. I'm going to analyze now the properties of this fixed point. So what properties of these fixed points do we need to analyze? We have to analyze the current because this is the main prediction of the Aharonov-Bohm effect, that there is a current. So we have to try to compute the current, which decays as 1 over the distance from the defect. And another thing is the normalization of this extended operator, which I call the quantum dimension. We call it G. So some people call it a quantum dimension, some people call it the defect entropy. It's some normalization of this defect, which is physical. And we proved almost 2 years ago that it's a monotonic function of the renormalization group on the defect. We proved it rigorously. I mean, as far as rigor is concerned in the physics literature. There is a relation between the quantum dimension and the current. You can prove that if you take a derivative of the quantum dimension with respect to the flux, you get the current. So there is a consistency check when you do these two computations, which look quite different. So this is the picture of the quantum dimension. So there are two fixed points. When you have a solenoid in the many-body system, there are two defect fixed points. One is a stable fixed point with a small quantum dimension, small but positive quantum dimension. And one is this unstable fixed point where the quantum dimension goes to infinity, exactly at pi, when phi over 2 pi is a half. And there is a renormalization group flow from here to here. So you should imagine renormalization group flow from the yellow to the blue line. And what are the currents? This is the current. So this is an analytic expression for the current at these fixed points. And the current vanishes at pi. So you see that it's very, very different from what we learned in quantum mechanics about the Aharonov-Bohm solenoid. Let me just emphasize the differences. First of all, the current vanishes at pi. Second of all, it's completely homogeneous. This defect is rotationally symmetric. And third, the current is maximized at some weird point with like quarter flux. Okay, so these are some properties of what happens when there is a boson moving around a solenoid. Are there any questions about this warm-up exercise? Yeah, so you can ask what is the meaning of this quantum dimension. So it's some kind of entropy that comes from the boson attached to the defect. Yeah. And you can check that there is an energy flow from the yellow line to the blue line, but not the opposite. It's also consistent with this because the stable fixed point only has irrelevant operators, while the blue line has so I'll go back. It's just this. So in the theory without a solenoid, this operator has dimension 1, and it's exactly it's marginal. And this shows that it's marginally irrelevant. As soon as you have a solenoid, this operator becomes relevant or irrelevant with some scaling dimension that I computed. Yeah, so the interaction, yeah. Okay, so this is the object that flows. Now let's discuss the main thing, which is the fermion. So it's very similar. You put a solenoid through a flat connection, but the main complication is that now there are several possible coupling constants at the solenoid, which I'll call U plus and U minus, because there are two components essentially in the Dirac fermion. So they could each have their own coupling constant, their own potential at the solenoid, and they both preserve rotation symmetry. Okay, so now the beta function is a little bit more complicated. The beta function is you have to calculate the beta function for both of these, and it's complicated now. Even though the theory is still free, it's somewhat complicated. I'm going to show you the results without going through the computation. So first of all, one important difference is that for the boson, without a solenoid, a contact interaction is marginal. For the fermion, without a solenoid, the contact interaction is irrelevant. For the boson, however, when you crank up the solenoid strength, the interaction becomes more and more irrelevant. And here it's the opposite. So as you crank up the solenoid strengths, the fermion interaction becomes more and more relevant. So it behaves very, very differently from the boson. So this is an example of the currents. So let me just explain what we find. There is, again, a fixed point which is stable. This is the blue line as a function of the flux. And this is the current, by the way. So then there is an unstable fixed point, meaning it's the fixed point with a relevant perturbation. You can flow to the blue line from the yellow line. And the picture essentially repeats a reflection symmetrically around pi. Pi over 2 pi equals a half. So the most important thing is that exactly at the half flux, there is a whole continuum of conformal filters. So that there is what we sometimes people call conformal manifold. The coupling constant U, this coupling constant has vanishing beta function at exactly pi. And it becomes an exactly marginal parameter. And there is a whole line of fixed points. So just to emphasize the difference from quantum mechanics again, we see that if we follow adiabatically, we can get non-zero current at pi if we follow the blue lines adiabatically. But there is a sequence of conformal filters with other values of the solenoid interaction with vanishing current, for instance, and they're completely homogeneous. So again, that's very different. And this is the quantum dimension. There is a conformal manifold at pi, which I cannot draw on this picture. So there is like a continuum of fixed points with G, which is the same, with the same value of G. But here there is an unstable and another stable fixed point. By the way, this number here is exactly the logarithm of 2, and it has some very interesting interpretation that one of the fermions gives a qubit, gives exactly 1 qubit to the solenoid. Okay, so these are the quantum dimensions for the fermion, and this summarizes the phase diagram for the fermion. Are there any questions about this before I go to the implementations on the lattice? Yeah. This defect is certainly not invertible, certainly. because it has, you see, a non-zero quantum dimension. Log G, for invertible defects, log G vanishes. And here the log G, it's a non-trivial conformal defect, so it's certainly non-invertible. Can we derive what? Fusion rules, yes, but I'm not going to present it here. And there is a group at NYU that has just put out a paper about it, and there will be a few more in the future. People are trying to understand how to fuse solenoids, and but yeah, I'm not going to talk about it here. But yes, it is accurate. Yes, so for instance, as I said here, you see the Hamiltonian or the action are quadratic, so the beta function is exact at one loop. And also this beta function is exact at one loop. So for the quadratic theory, everything I'm saying is exact. So in an attempt to how can we test these predictions? There are many models on the lattice. This is graphene, for instance, in graphene, where people have already developed the technology to insert a solenoid. This model is called the pi-flux model. It's an old model for quantum Hall transitions. And we know how to insert solenoids. You can also solve it on the computer. These are both bipartite lattices. They're exactly that you can put them on the computer. You can solve it. You can even solve it analytically in some cases. And so one thing that we've been trying to do is to reproduce the field theory predictions for the currents and for the response of these systems to solenoid by solving these models. So this is still going on. I'll tell you at the end of what the status of this is. Now I want to just mention one theorem. For those of you who work on topological filters, this might be interesting. I'll go through that quickly. If you were attentive, if you were noticing what I was saying carefully, in all the examples that we had, the log of the G function was positive. Also in the boson phase diagram, the quantum dimension was positive. In fact, this is not generally true for extended defects. There are many extended defects that are known in the literature where the logarithm of the G function is negative. So we have a conjecture that defects of this particular type, which are codimension 2 boundaries of codimension 1 nether charges, must have a positive quantum dimension. So that's a conjecture. Well, conjecture, and there is an argument for this conjecture that is almost a proof. I'm going to explain it now. It's a general theorem that's useful in understanding which phases these defects can be in. So the theorem is that G is bigger than 1, and therefore log G is positive. That's the conjecture for symmetry defects. So the way we're trying to prove that is that we map the defect conformally to hyperbolic space times a circle. This is the map. This is the geometry in cylindrical coordinates around the impurity, around the solenoid. This is a conformal transformation. And now the solenoid, what it does in these coordinates is that it adds a chemical potential on the theta angle. And you can interpret this theta direction as essentially the time direction in the thermal field theory sense. So then you just have to use the fact that partition functions of theories with chemical potentials cannot be bigger than the partition functions of theories without chemical potentials, because once you add the chemical potential, you can only decrease the partition function. And that is almost enough to prove that the logarithm of G must be positive. You need a few more steps because this is the space here has infinite volume. So thermodynamics is subtle. You need to regularize the thermodynamics. But with a few more steps, I think you can prove that all the conformal defects of this type have non-negative logarithm of G. Okay. Okay. Now, a more general question, other than inserting these solenoids, is how to understand crystalline defects, such as disclinations and dislocations. Disclinations are just conical defects of the crystal. I'll show you some pictures. And dislocations are a little bit harder to explain. Now, when you have a lattice system and you have a defect, it doesn't mean that it's going to look exactly the same in the quantum field theory limit, because there is potentially a non-trivial map between the lattice symmetries and the continuum symmetries. This homomorphism is potentially non-trivial. So when you make a conical defect in a crystal, in a continuum limit, it might look like a conical defect plus some solenoid. And that's why I spent all this time reviewing the dynamics of solenoids. It will be important for what comes. So a very important conceptual issue is that when you have a conical singularity with or without an Aronoff-Bohm defect, the whole thing preserves SL2R symmetry. So the whole point is that conical defects at long distances flow to conformal defects. So we saw conformal defects of one type already, which are solenoids. Another very important class of conformal defects are conical defects that you just make, they put a quantum filter in a cone. And because the cone preserves conformal symmetry, the infrared should be a conformal defect. So there is a question now about what is the infrared limit of a quantum filter in a cone. And at the tip of the cone, there may or may not be an additional solenoid. So here, I just wanted to show you some things that you find for the fermion on a cone as a function of the solenoid. So one remarkable phenomenon is that there is an enhancement of the current in the stable fixed point. So there is some current due to the Aronoff-Bohm effect, but it turns out that the conical singularity enhances it if it's a deficit cone. On the other hand, when there is an excess angle at the cone, something even weirder happens, that even without a solenoid, there is a spontaneously generated current. And that can be tested experimentally. So when you prepare a conical angle with negative curvature, it turns out that there are conformal fixed points with currents, spontaneously generated currents out of the blue. And that is very strange, but it is true. So let me just summarize the main two properties of the conical conformal defect that I mentioned. First, it leads to enhancements of currents. In general, there are many fixed points for cones. The beta functions are very complicated, and there are many fixed points. You see here many fixed points, at least 4 different fixed points, some conformal manifolds. So the beta functions of cones with solenoids are very rich, and there are many fixed points, even for free field theory. And we've also found that some fixed points have currents, even when there is no solenoid, weirdly enough. Okay, so now the question, can it be verified? So how do you prepare a cone? So on the computer, it's very easy. You just take your favorite lattice system, you cut out a wedge, and you glue the rest. Okay, you put it on the computer, you try to simulate it, and that's a nicer picture that we prepared. So you glue, you have a conical singularity. Automatically, there is a solenoid in this model, because this is one of the models where this homomorphism rho is non-trivial. So when you make a conical singularity on the lattice, it leads to a solenoid in the continuum language. And so we've been trying to verify the predictions. This is for the case that there is this is in the case that there is a disclination with positive curvature. So it's this picture. And we've been trying to measure the currents. And indeed, we already see, I'm going to explain what you see here, but we already see that there is an enhancement of the current due to the conical singularity. We are not yet at the point that I can say that it completely agrees with the field theory prediction. There is some numerical mismatch, but the qualitative effect is already present. So we see this little effect here that there is an enhancement of the current. So this effect we can already see qualitatively, but not quantitatively. We're still working on that. And now I wanted to summarize. Let's see. I'll have 10 minutes for questions. So the solenoid defect is a very rich defect, mostly because of the contact interactions. You have to understand how to renormalize contact interactions with the solenoid. And there are many fixed points with properties that make it very different from quantum mechanics. So there are examples where there are currents in the vacuum, with or without a solenoid, and bosons and fermions react very differently. So another thing is that there is this normalization of the defect, which is called the defect entropy or the quantum dimension. And there is a conjecture that the logarithm of G is positive, and I gave some argument for that. This is super relevant for graphene because there is already an experiment. There is already an experiment with this implementation. It's very easy to implement in graphene. So it will be important. It will be nice to see that what I said here is borne out in an experiment. That's exactly the situation that there is a conformal manifold. So the defect coupled constant becomes exactly marginal. And finally, I mentioned that there is the subject of matching crystal symmetries to their continuum limit. So when you have a crystal with electrons, you go to the thermodynamic limit. It looks like you're in a continuum field theory, but the mapping of the symmetries is non-trivial. So disclinations may be attached to solenoids and so on. But you can, yeah. So in field theory, it's possible to formulate, and it flows to some conformal defects. So there is a notion of a conformal field theory on the cone, and the cone preserves the conformal symmetry. So there is a very clear low energy prediction for the phases of these models. And thank you. That's the summary.
For next talk, and we are welcoming any questions.
Is that I'm telling you, I should when the operator. So this is the reason was asked what is the principle you
Um, you're talking about this model, right? So it's a quadratic theory. Due to the solenoid, some of these operators are irrelevant. So in the infrared, they flow to zero. You can ask, what if I insist on adding them anyway? And you can try to flow to the UV. Sometimes it's possible, and sometimes we don't know. So in some cases, we know the answer. In some cases, we don't know the answer. There may be superconductivity, for instance, if you start flowing up the UV to the UV with these contact interactions, because it may create a bound state, and maybe there will be a 2-point condensate. So there might be a condensate or something like that. Yeah, so we usually don't discuss this question of what happens if you are trying to flow even more to the UV than this unstable fixed point.
Any questions?
Describe in more details the graphene setup discussed in the last section.
Yeah. You mean I didn't cite the relevant papers? I'm sorry, I'm going. I didn't cite the relevant papers in the slides. I'll be happy to send you the references via email if you send me an email. But the point is that it is essentially true that if you make a hole in graphene just by hitting it, it's essentially true that you generate pi flux, a pi flux solenoid.
It's because of the graphene background.
Um, eh, I wouldn't say it's because of the band structure. It's just because of well, I wouldn't say the band structure. I think I can just send you the reference. You'll see what's the implementation. What we've been doing when we don't actually have an experiment. We're trying to check these predictions in simulations. So what we've been doing is that we just put this bipartite lattice on the computer with a simple hopping model of hopping electrons. And then we're inserting a flux essentially in this way. So let me show you the slide. I did essentially this way by by multiplying the hopping parameter by a phase like I on some line, but not an infinite line, a half infinite line. And then the origin of this line is essentially a solenoid. So the origin of this line would be essentially a solenoid.
So it's like it's a things this flux by hand.
Yes. In our attempt to verify the theory predictions, that's what we're doing.
Can you give some physical information for why there's a curve when the magnetic field? Does it appear both in the bosonic and fermionic?
No, it doesn't appear in the bosonic theory. So I don't know why we still don't understand why that is the case. So let me show. I didn't put the diagrams for the bosons. For the bosons, though, there are two fixed points, two defect fixed points, and the only one which has a finite quantum dimension and is actually reachable in experiment has zero current because you see the derivative of the G function vanishes here. So it's very different even from the quantum mechanical Aronoff-Bohm effect. And when we studied a little bit what happens on a cone for a defect, for a cone for a boson, and I don't think we found cases where there is a current without a solenoid. Now it doesn't actually contradict anything because I'll show you the picture for the cone. You see there is when there is an excess angle, there is a fixed point with current, one fixed point without a current, and a fixed point with the opposite current. These are unstable fixed points. Both of them are unstable fixed points. So they require some tuning. But it means that you just tune the potential at the origin. You don't put a solenoid. You just put the potential, just tune the potential at the origin. And remarkably, for some values of this potential, the fixed point has a current. And that's very strange. We don't understand it yet.
In case, I wonder how the RG flows behaves between the stable fixed point and the unstable fixed point.
It is possible to compute. It is possible because everything is quadratic. It's complicated but possible.
But I just wonder, you have a cosine picture there, so I found that a stable fixed point and
Yeah, so this picture is not the G function. This is the current.
the G function.
Oh, you're
You
okay.
have a cosine picture.
Okay. I have to go to
Yeah,
this.
for this one.
Yeah,
So
so
suppose that you have some RG flow between these two. I just wonder how the G theorem, is there any G theorem in here?
yes, the G theorem also. This is how we actually discovered the conformal manifold. We know that this can flow to this. And then we said, so how is it possible that this will be true even at pi? Because they have the same G function. So there cannot be a flow. And what was the resolution? This was a paradox for like a few weeks in our project because it contradicted the G function. The resolution was that there is a line of fixed points. And if you go back to this picture, sorry, I keep confusing. If you go back to this picture, it means that actually at this point, there is a continuum of fixed points. And this continuum of fixed points are the contact interaction strength. So the yellow point, if you follow the yellow adiabatically and you follow the blue adiabatically, you reach different contact interactions. But at that special point, you can change the contact interaction as an exactly marginal parameter without changing the G function. And once you go to this side, it reverses and the flow goes like this from up to bottom. So the only way that this diagram, the only, yes, so the G theorem is satisfied, and the only way it can be satisfied is because the contact interaction at this point becomes exactly marginal.
Yeah, I see. Thanks.
So usually we think that contact interactions in 2+1 dimensions are irrelevant, or marginally irrelevant, I mean. Here it becomes exactly marginal. That's the main point.
Thanks for Professor Zohar.